What's up, guys? Today I wanted to make a quick video about profiling Rust programs. So first of all, what is profiling? Well, profiling is basically the answer to the famous computer science quote that premature optimization is the root of all evil. So how do we know if optimization is premature or not? Well, the main thing we have to answer that question is profiling. So today I'm going to talk about both CPU profiling and memory profiling in the context of two projects I've been working on lately. So you'll see here I've got pulled up my make file for one of my projects called ANPAS. You can find the repo here if you're curious. And this is basically a program for least squares fitting and stationary point determination. So this basically takes big polynomial systems of equations and finds the least squares solution to the system. And we use this in our coordinate force field chemistry research. Now, what I'm showing here again is the make file. And you can see I've defined this macro that first runs cargo build release with whatever bin we pass as the first argument. And then it's going to run valgrind with the tool callgrind on that. And we've got some extra options we pass to valgrind, eventually generating this callgrind.out file. And you can see down here I've just defined a few other recipes that call that macro on different binaries in my source/bin directory. So now if we switch over to the terminal, we can call this. You can see ZSH filling it in already. If I call make profile.fit, what this is going to do, again, it will first compile the fit binary I've written, which we can look at over here. Source bin fit looks like this. It's just going to load an ANPAS from a file, and then it calls the fit method on it. And then once it's done that, it will run valgrind. So I'll go ahead and start that running. This might take a second, so I'll just go ahead and talk over it. So again, we can see what is ANPAS.fit doing. Well, it's doing some a matrix initialization, so it makes this X matrix. Then it goes through, you see we've got these three nested loops here. It's setting up X. And actually, I remember now that I can show you exactly what it's doing in terms of some more mathematical notation. So what we're doing here, hopefully the PDF will clear up, is this operation right here. So we're building xik as the product over j of this little xij to some exponent. So again, we're expanding some kind of polynomial equation here that eventually looks something like this. Okay, and then once we have that assembled, we do some matrix math. So we've got xtx is x transpose x, and then we invert that, multiply it by its transpose, and do another multiplication. So with all that in mind, now that we've run valgrind, you'll see that we have this callgrind.out file. The way I usually visualize that is with kcachegrind. So this is a graphical application that gives us a lot of information here. Now hopefully, can I zoom in here? This might be kind of small, but first of all, you can see down here we've got this kind of flowchart. So if we look at this, we can start clicking on the flowchart. Okay, anyway, I'll try to blow this up later. So you can see we can just start clicking things. So here's main. We got main, main. We've got some little start things. And we can also navigate over here. What we're looking for are things that have spent a lot of time. So again, this is CPU profiling. So we want to see where the largest fraction of our time is being spent. So we see that almost 95% of the time is actually in the fit method. And if we go down, we can start to look through here. Now you'll see 22% of the time is spent in this invert function. 18% of the time is spent in powidf2, so that is an exponentiation function. And then 35% of the time is spent doing matrix multiplications. Now, I had been looking at this profile basically for months and thinking, well, what can I really do? I mean, the algorithm says I have to invert the matrix, I have to do these multiplications, and I have to do these exponentiations. But this shows one option for how you can speed up code. So Actually, I'm going to show two examples today. The first way you can speed up code is to find like little things that you're doing that are kind of silly. So to spoil things a little bit, if we think about exponentiation, there are some cases where exponentiation doesn't really make sense. For example, if you think back to the equation I showed, or just what we're doing here, is we're taking the product. So if we were to multiply here, if we were taking the product and one of these numbers were 0 or 1, then we don't really need to do this multiplication. And how might this end up being 0 or 1? Well, first of all, if xik is already 0, we can skip it entirely. If disp is 0, then whatever power we raise it to will still be 0. And if this power is 0, then we're just multiplying by 1. So those are some small things we can change. Now, on the other hand, as I mentioned, the algorithm I'm using here requires this matrix inversion. And it also requires all of these multiplications. And you can see we're spending a lot of time in that inversion. So where you'll find a lot of benefit sometimes is doing these algorithmic changes. So if you can switch to an algorithm with a lower time complexity, that's where you'll usually get really big wins. Now, to give you a bit of a taste for what this problem is actually doing, I think I mentioned before, but it's doing ordinary least squares regression. And if we scroll down to this matrix vector formulation, this is basically what we saw in that PDF. And the equation that we're evaluating is this right here. You'll see we've got xtx, you'll see the inverse, and then you'll see the last two multiplications that give us our coefficient vector beta. So this is what I was thinking that my algorithm was restricted to. This is just how you do it. However, if we jump down to this see also section, you'll see that there's actually a numerical methods for least squares. So if we click on this and you scroll down a little bit, we'll see the same expression here, and it says that this equation is correct and can work, but it is not computationally efficient. So as soon as I saw that, I knew I was on the right track. If we scroll down a little bit farther, we can see that if this matrix is well conditioned and positive definite, then we can solve them using the Cholesky decomposition. Now, I was already using the Cholesky decomposition to invert my matrices, so I knew that this was the case. So by implementing this new algorithm, you'll see that we just do a couple substitutions and a final solution, or two solutions here, and we end up with the same answer. So if I hop back over here, I can go ahead and close this for now, and I've actually already implemented this. So we'll just do maggot checkout master, and I'll check out this commit here. So you should see this code update. You'll see now that we have just X transpose, we have this one product, and then if we go to this new solve least squares function, you'll see that we've implemented the new algorithm I showed you a second ago. So we do the Cholesky decomposition, we solve this part, transpose it, solve again, and then we just return the answer. Now, if I run my make profile.fit again, we're going to see something a bit different. First of all, you'll notice that ran faster, and now I can do cachegrind.out. You'll see we're down to 91% spent in fit. The invert is completely gone, with only 4% now in this Cholesky part. Our time spent doing multiplication is actually down, and you'll see that the exponent now accounts for even more of the total time we spent. Now, doing that exactly doesn't necessarily, it doesn't give us a really nice picture of how much time we were spending before and after. So in addition to using callgrind and valgrind like this to generate this cachegrind output, another thing I like to run is this tool called hyperfine. And you'll see if we run this, that it's running our code over and over and giving us this estimate at how long it's actually taking. So again, what we're looking at here is the new version of our code. If I go back to here and I check out this version again, and we recompile, let let's see, we're going to do cargo build release. And we run hyperfine again. You'll see that it used to take closer to 26 seconds, or milliseconds, plus or minus 1.3. So you can see right away that we've taken off about 30% of the time. And I know from my previous look at this, that if I bump this up to C5H2, then this takes about something like, I think, 10 or 12 seconds, and this takes closer to 5 seconds. So the good news is that it looks like our improvement actually scales even better as the size of the system goes up. So there we go. That's basically the end of our CPU profiling. Now, the other thing I promised to show you is that if we mag it, check out master, and we go back to librs, let's jump down to fit again. So if you remember, the other big place that we were spending time was doing this exponentiation. And that actually began to dominate even more after we made our first change. So you'll see here that the code changed a little bit, and I'm doing what I alluded to earlier in the video. I'm actually checking for some of these cases where we may not want to do the exponentiation at all. Again, if xik is already 0, or the thing we're about to multiply by is 0, or our exponent is 0, then we don't need to do the multiplication itself. So you'll see I also pulled out some other things here. So we're doing this array reference once, we're doing this reference once, I'm pulling out this row. All of these are making pretty negligible changes. This was the big thing. Now, one thing to note, and again, getting back to our premature optimization quote, you actually need to test to see if things like this help. Because in many cases, adding a new if, a new condition, a new branch that has to be checked every time code is entered can actually slow down the resulting code. So it was not guaranteed that this was going to help. And in fact, I believe there are other parts in this code where I've taken things like this out because it was actually faster to do it every time than it was to check whether we should do it every time. But anyway, once this change is made, we can recompile again and run hyperfine one more time. So actually in this case, it's running a little bit slower, but I think that's just because of the the fact that I'm recording the video. So that is a final point to make when you're doing, especially CPU profiling, is that really ideally you should be running these benchmarks on a nice, quiet machine, maybe some kind of server you have somewhere else, not running things like OBS and Emacs and web browsers and stuff like that. So especially these small or micro benchmarks running here are really sensitive to the other things running on the machine. But anyway, if we run one more time, we can do our make profile.fit. And if we look at this again, we'll see that we are now spending far less time doing this actual exponentiation, which makes sense. We're not doing as many of them. But we are going to be spending a little more time doing this kind of comparison. Now, what I've pulled up here on the right while that was compiling is the little table. And I often do stuff like this when I'm benchmarking. You'll see I'm trying with both this C3H2 test case and the larger C5H2 test case. And as I mentioned, the original formulation took about 14 seconds on this one compared to 6 seconds on the new version. And then when you do this, this skipping 0 and 1 in the exponentiation case, you can actually get it down to about 5 seconds. So apparently I hadn't actually benchmarked it with hyperfine for the C3H2 case, but I did see that on the larger molecule, this difference, this made a big difference as well. Okay, so we've covered hyperfine and valgrind for CPU profiling. Now I want to move over to looking at memory profiling. Okay, again, you can see I've defined one of these macros, and this time The first part looks pretty similar. We're compiling with debug symbols, but in release mode. And this time we're going to be using the heaptrack tool. So unlike before where we had to use valgrind followed by callgrind, heaptrack in this case is actually both the profiling tool and the visualization tool. So all I have to do here is pop open a terminal, zoom in a bit for you guys, and I can say make memprofile.cart. Now this one will actually take a while, so I'll probably pause the video. But the point here is that now we're going to be looking at our memory usage. Before we were looking at CPU usage, or effectively time usage in the code. This time we're checking the memory. And notice in both cases we're relying on these external profiling tools. Now in this case there's actually a pretty obvious place where I know I'm using a ton of memory, but in the other case it wasn't obvious at all. Alright, now you can see that this actually finished already, and again, let's see, can I zoom in? It's sad that you can't zoom into these. But you'll see that the major columns here are peak contributions. So this is our peak memory usage, our largest memory leaks, and then we can also look at what's allocating the most memory and the most temporary allocations. So you'll see here that our peak heap memory consumption was 12.9 megabytes, and that we leaked a total of 475 kilobytes of total memory. Now, what I usually jump to when I'm looking at, what is this called? Heaptrack, is usually I'll jump to the flame graph. Now, if you haven't seen flame graphs before, basically what you're looking at is just a stack of functions, and their width is how much they contribute. So you'll see if I hover over main, it says that it had an 89.1% contribution to peak memory consumption. Now everything above it is basically called from main. So if I click on RT laying start internal, you'll see that it within main accounted for also 89.1. Catch unwind is the same. And let's keep going up until we hit one that's actually our code. Now here we go. This one is actually my code, and this is basically the main entry point of my code. So chord type run. If we hop over here and actually look at bin cart, you'll see that basically what it does is call run somewhere right here. So this is the main part of the code. Now inside of run, we see that first part, cart colon first part, is using most of the memory. And within that, it kind of divides in two. So the first thing we look over here is actually this iterator collect. So if I go and narrow this to definition, and I just search for collect, this collect is using 37% of our peak memory. But on the other side, even more than that, is this one. So this call to finite difference build points is using 43.8% of our peak memory. So I can go in here and look at build points if I want. Now, I actually know that this is a bit of an issue, and I mentioned this on the last PBQFF live stream, because what build points is doing is generating all of the points for the whole quartic force field, and in doing so, it is building what I called aptly a big hash. So what this is basically a hash map of every geometry and all of its symmetry equivalent structures. And every time I'm thinking about building a job, I check this big hash map to see if that geometry has already been inserted. And you'll see here, big hash insert is one of the big things. And the reason for that is if I look for big hash and we jump to the insert method, you'll see that it's calling to keys, which takes some reference to a molecule. It allocates a new vector and basically clones all of this into some format used by the map. So we are just building a huge number of these geometries, storing them in the hash map, and then we actually keep that around all the way out here. So this actually gets spit out, target map, and we still need target map all the way down here. Actually, you can't see it here, but when we return from first part and do the second part, we're actually going to use that map later. So as I mentioned in the PBQFF stream, I have a couple of ideas for fixing this. So first of all, there's not really any reason to have both of these around at the same time. Like, basically this target map gets used to build the jobs, and then we use the jobs later. So it would make some sense to basically have an iterator idea here, where these are initialized lazily. So we get some targets, we turn them into jobs, we run the jobs, and then we keep calling each of those in sequence. We don't build all the jobs, or we don't build all the structures, build all the jobs, and then run all the jobs, because that requires keeping all of this memory around at the same time. The other idea here, because the reason I went with this approach in the first place is that it was much easier to implement. So it's a lot easier to think about it in these steps. Like, I do all this at once, then I take those that I already built, I filter them and do something else to them. So I do it like stepwise transformation rather than doing, I do like some of the work here, ship that off, do some of the work, ship it off, do some of the work. Which should be much more memory efficient. Like, we're getting this big peak where we've built all of these and then they just hang around. So that's an idea here, to use an iterator. The other idea is to simplify basically what I'm storing here. So I'm storing like whole molecular structures. It feels to me like there should be some simpler representation here where I don't have to store so much at one time. So that's another idea if I do want to keep the same algorithm. But anyway, today's video is a little bit more about the tools. So hopefully you can apply heaptrack to your own code and find some memory issues. I have certainly found some issues, but it's a little bit harder to fix this one, I think. It's going to take a lot of work, a big refactor, to get rid of this. But anyway, hope you guys enjoyed the video. Go out and write some fast code that doesn't use too much memory. I guess the last thing to say on that note is that sometimes memory and time are tightly intertwined. So if I were to run the CPU profiling I did, I would probably see that I'm actually spending a lot of time generating all of the structures I'm putting into the big hash. So it's not just using a lot of memory, it's also using a lot of time. And writing things to memory, retrieving things from memory, those take time as well. So in a lot of cases, the more memory you use, the more time you're going to take as well. So although heaptrack is primarily a memory profiler, when you fix a lot of these issues, you'll end up fixing a lot of other issues too. So again, go out, use valgrind, use heaptrack, use hyperfine to benchmark your own code, find the bottlenecks restricting your performance, and optimize them. See you next time.